Alright, so here we are looking at section 11.6, which is about geometric probability. Of course, if you don't know, probability is a number between 0 and 1 that represents the chance that an event will occur. Right, so somewhere between 0 and 1, some decimal fraction is going to determine what the chances are that some event is going to actually happen. So an event with a probability of 0 is one that we would say will not occur, and an event with a probability of 1, we're saying it's certain to occur. So the closer we get to 1, the more certain we are that it's going to occur. The closer it is to 0, the less likely that something is going to occur. So with geometric probability, we can do probability in length. And so if we let AB be a segment that contains segment CD, so I've got AB here, and it's got segment CD in it, and if a point K on AB is chosen at random, then the probability that it is on segment CD is as follows. Point K is on CD, the probability of that is going to be based off of the length of CD, which is just a portion of AB, over the entire length of AB. So when we look at this probability, what we're really looking at is the part over the whole. Right? So whatever part that we're looking at the probability of it happening in, divided by the entire length, the whole item. Right? So K could end up anywhere on there if we just randomly put a dot there. And we're looking at the probability that it's going to be in between CD. All right, so we can do a probability with area. So let J be a region that contains region M. If a point K in J is chosen at random, then the probability it is in region M is as follows. The probability of point K is in region M is going to be the area of M. All right, so we're going to base it off of what the probability is that this area right here in M, that K would be randomly selected inside that area. So if we're just like throwing darts at the board, the chances that that point ends up in M is going to be based off of the same idea we did with line segment AB. Right? Area M is the part that we're looking at, and area J is going to be the whole. So the part divided by the whole. If you can get that under your belt, then you'll be able to maintain the right idea of what you need to do to find the probability. So with that said, moving on to the next page, which actually has some examples. Each circular hole has a radius of 0.5 feet. If a beanbag is equally likely to land on any point on the target, find the probability that the beanbag goes through one of the holes. Alright, so here we've got basically, looks like a carnival game, throwing beanbags, trying to get it through the hole. And we've got 4 holes, each one with a radius of 0.5 feet. And then it's in a rectangle that's 3 foot by 4 foot. So remember, our probability is still going to be the part divided by the whole. So the part in this case is the 4 circles, and the whole is going to be the rectangle. So the area of the rectangle, of course, is length times width, so 4 times 3. It's going to give us 12 feet squared. And then from there, we need the area of one of the circles, which they're all exactly the same. So we're going to say area of the circle is pi r squared. So we're going to do pi times the radius, 0.5 squared. And if we square that, going to give us 0.25 times pi, and ultimately 0.25 times pi will be 0.785. Now that's just one circle, and so we've got 4 circles. So we're going to say 4 times 0.785. It's going to give me 3.142. So this is our part, and the rectangle is our hole. So our probability is going to be 3.142 over 12, and 3.14 divided by 12 is going to be 0.262. It's going to be our probability that that happens. So it's a fairly small number, not real close to 0.1, or not close to 1, so closer to 0. So the likelihood of getting that is fairly slim. All right. So next one says you ride to work on a bus. The buses come every 15 minutes, and the ride to work is 31 minutes. You arrive at the bus stop at 8:24 a.m. What's the probability that you will be at work by 9 a.m.? All right, so you want to be on time to work. You need to be there at 9. So I'm going to cross out this first line because it really has no weight on what we're doing. We just want to look for the numbers and how they apply. So we basically want to go from the bus stop to work. So we got this distance here. Now it tells us that the time to get to work is 31 minutes. We arrive at 8:24, and we need to be there by 9. So from 8:24 to 9 is a time length of 36 minutes. So we got 36 minutes to get to work. The ride to work, it tells us, is 31 minutes. So what's left is a total of 5 minutes that we can wait. All right, so that 5 minutes is our acceptable wait time. So if our acceptable wait time is 5 minutes, buses come every 15 minutes, then 5 minutes is the part of the time that I can wait, but 15 minutes is the whole, the possible time that I could wait. So to find the probability, that's going to be 5 out of 15. And if we divide that out, it's going to be 0.333. So still not a great probability that we're going to be on time. It's a higher probability that we're going to be late. All right, so now moving on to the last one. The shaded area in the diagram of your backyard below shows the area that you can see from your window. If a child is equally as likely to play in any part of the backyard, what's the probability that you'll be able to see him from the window? So your window's here in your house. This is looking into your backyard, and from where you're at looking through your window, you can see everything that is in the green section here. So we want to know what the probability is that your kid will actually be playing in this green area and not in one of the other areas that you're unable to look out and see. So comes back to the part over the hole. So we need to figure out what the measurement of the hole is, and then we need to figure out what the area of the part is that we would be able to see them in. So the hole, which is going to be the area of, in this case this is going to be a square, because if I add 27, 5, and 32, that's going to give me 64. So my backyard is 64 feet by 64 feet. So I need to find the area of the square, which area of a square is just the side squared. So 64 squared, it's going to give me a total of 4,096 square feet. And then in order to get the area of the part, I'm going to use these triangles, because this is a trapezoid and I really don't know all the lengths of these two sides. So it's going to actually be easier for me to go ahead and find the area of each triangle. Because it's 64 by 27. This one will be 64 by 32. So I've got two triangles to find. So area of triangle 1 is going to be 1/2 base times height, or 1/2 of 27 times 64. And so if I put that into the calculator, it's going to give me 864 feet squared. Now I need the area of the other triangle. Area of triangle 2. That one is 1/2 of 32 by 64. So multiply that out. It's going to give me 1,024. So in order to figure out what the area of the green portion is, I need to subtract these two measures of the triangles away from the whole area of the square, so I know what's left being the shaded part. So the area of the shaded is going to be equal to area of the whole backyard, 4,096, minus the parts that are not shaded, which is going to be 864 and 1,024. So 4,096 minus those two added together, that's going to give me 4,096 minus 1,888, which, subtract that out, that's going to be 2,208 feet squared. So now this is my hole, 4,096, 2,208 is my part. So when I look at the probability, it's the part divided by the hole, or 2,208 divided by 4096. Which is going to give me a probability of 0.539. So I'm a little over 0.5, so there's a slightly higher probability that I will be able to see my kid in the backyard than the probability that I won't be able to see. So that concludes section 11.6. I hope you understood it. If not, please watch this again, and we'll see you next time.